All right, so we're going to solve this problem with no voltage method. In this problem, we have two voltage sources and a current source. Okay. Now, generally speaking, the more voltage sources you have, the more you want to do no voltage method. The more current sources you have, the more you want to do mesh current method. It's kind of the way it works. But it doesn't really stop you from doing one or the other. You can solve this problem with mesh current method, and it would be just as difficult or just as easy, depending on how you like to see the situation. The first thing I'm going to do is I'm actually going to remove this ground from this center node. You can solve the problem with the ground on the center node. I'm just not going to do it because it actually makes the problem more difficult than I think it should be. Instead, what I'm going to do is I'm going to put this ground on my node 1 or my node V1. Okay. Now what that does is it attaches the node directly to my voltage sources. And when you attach your node to voltage sources, or your ground, excuse me, when you attach your ground to voltage sources, it actually automatically creates values for the other nodes that are attached to it. So what do I mean by that? By attaching V1 to the 8-volt source, I automatically know the voltage of V2. Okay. By attaching, except this, by attaching V1 to the 12, I automatically know the V3. Okay. So that's what we're going to do there. That's why I'm going to move it. Also, this is a screenshot, so please pay no attention to this little plus. Our goal in this problem is going to be to find the voltages of V1, V2, V3. Now, because I kind of got rid of my ground there, I have to rename this node. I'm going to rename this node V4. Okay. And so now instead of finding V1, V2, V3, I'll find V2, V3, V4. That's not really a big deal. So when it comes down to doing the no voltage method, our steps are as follows. Step 1, we're going to label the ground. I think I'll put that in, put it like this. Let's see what we can do here. I'll put a text box. Yeah. Step 1, we'll label the ground. Okay. We'll also label nodes and currents. Okay. Maybe not label the ground. Let's just say place the ground. That's a better way of saying it. We place the ground because you're able to kind of put it wherever you want. Then you label your nodes and your currents. So that's going to be step 1. Okay. So that'll be our step 1. Step 2 will be to solve or analyze, I guess you could say. Analyze your voltage sources. V sources. Okay. Boom. So that'll be step 2. And we'll do that in 1 second. So I'll move that over here. And I'll put my 2 and we'll put my circle. All right, great. Labeling my ground, I'm going to then label my, I've labeled my nodes, but let's put some currents on this bad boy. I'm going to assume that this current goes like that. This current goes as such. And this current comes like this. You don't have to draw them in this way. It's just that that's the way I think they're going to go. And so you just put what you assume, and then you work with how you assume it. And then everything else will fall into place. Okay. Negative numbers mean negative numbers. Positive numbers mean positive numbers. Negatives, your guess was wrong. Positive, your guess were right. Of course, that depends if you've done your algebra properly, but I'm going to do my algebra properly. So from here, step 2, we're going to analyze our V sources. So what does that mean? I have 1, 2 voltage sources. So I'm going to look at them both individually. First thing I'm going to do is I'm going to look at my 8-volt source. So I say, okay, for my 8-volt source, you always want to do the plus term minus the minus term, okay? So the plus is sitting on the right, the minus is sitting on the left. That plus is V2, that minus is V1. Okay, remember with no voltages, with no voltage, your voltages don't sit on the element, they actually sit on the node and go across the element. So think of it as this this plus is not actually on the 8, it's not actually on the battery, but the plus is actually over on this side. So the plus is here and the minus is there. So now we can associate the plus with the V2 and we can associate the minus with the V1. Okay, so that's kind of the way to think about it. So we're going to do plus minus minus, and so it's always plus term minus minus term. It's always positive minus positive polarity minus negative polarity. So the plus will be V2 minus the minus will be on V1, And that's got to equal what the voltage source is. We're working with 8 volts. And so we got to say that equals 8 volts. But then, of course, you got to keep in mind that your ground is where your V1 is, and your ground is 0. So what that means is we simplify our equation to get V2 equals 8. And it's for that reason that I ground the voltage source. If I never grounded it, I would have had an equation. Okay. And that means that I would have most likely had to do a supernode, and I'm not about that life right now. It's not to say that you will never have supernode problems. It's just to say that if you can dodge supernodes, then dodge supernodes. Some are undodgeable, some aren't. This one is dodgeable. Second, I'm going to do my 12 volt source. The plus value is on my V3. The minus value is on my V1, and it equals 12 volts because that's the voltage of the source. The same exact thing happens. These are both grounded by the ground, and so they both get that simplification factor. So I know V2 automatically, and I know V3 automatically. Okay, so I got 8 volts and 12 volts. Great. So with that being said, I actually automatically know this voltage, and this voltage. This is 12, this is 8, this is 0. Last but not least is my last node, V4. So finding V4 is going to be my last step. Unfortunately, I ran out of voltage sources, so that's okay. I'm just going to move to step 3. So step 3 would be you're going to do KCL at your other nodes. Okay. Write your equations. In node voltage method form. Okay. So that's going to be how we do that. And I'll put a little space right there. Boom. Shrink it. And bam, that's where our step 3 is. Okay. So that's going to be our step 3. So what step 3 looks like is what I'll do is I'll move this whole picture down. It wasn't enough. There we go. Move this whole picture down. And then I can work with it from there. So at step 3, you look at your situation. You look at the KCL of the node that we haven't touched. And V4 is the only node that we haven't touched. So we say, okay, at V4, at node 4, whatever you want to call it, look at your situation. You have this guy. So the 10 ohm current going in. So I'm going to say we have I10 going in. Okay. Then you also have the I5 going in, the current through the 5 ohm. But then the current through the 4 ohm is leaving. Okay. And so you have to make that a minus. We're just setting up a KCL equation. All that equals 0. What goes in must come out. 10 and 5 go in, 4 has to leave. All right, no problem. Now, that'd be great if you were just doing KCL, but we're doing no voltage method. No voltage method is just a fancy way of doing, well, I should say a more complete way of doing KCL, okay? So we're going to convert our KCL equation into the no voltage rendition of it, okay? Remember this, currents always go from the plus term to the minus term. Current goes from plus to minus, So that's going to be the way we kind of think about it. I'm going to erase all of that, of course, because it's just a lot for me to have on one diagram. But if you think of it as the current goes from the plus to the minus, and remember, let's just use a 10 first. It'll start on the plus here, and then it'll end on the minus there. So the plus is touching V2, and the minus is touching V4. So I10, you can write it as V2 because it starts on the plus, minus V4. We know I equals V over R. So V2 minus V4 is going to be the voltage, and the R is going to be 10. And that's how you write the current for the current passing through the I-10, okay? So I did too much and I can't backtrack. So I'm just gonna have to rewrite all of this. Blank this out, put my V4 here. All right, cool. And then put that, bam. So that's gonna represent, all of this represents that I-10. You do the same thing for the I-5. So you put a plus, I-5 starts on V3 and ends on V4. All right, you could think of it as plus minus or start stop. It doesn't really matter. You're gonna hear me use them interchangeably because I see them the same, you know. So if it starts on V3 then you say it's V3. It's always a plus term minus a minus term. V3 minus V4. And then you have to divide it by the resistance, 5. Okay? Now, mind you, this is current. These are voltages, but the entire group does represent current because I is V over R. Okay? And a lot of students kind of mess it up. When you have just V2 minus V4, that's voltage. But V2 minus V4 divided by 10, that whole group is the current. Okay? You're going to do the same thing for I4. Keep the minus in front because remember, it's coming from the KCL equation. The minus isn't special. It comes from the fact that that current's leaving. But you're going to do the exact same thing. The start is on V4 and the stop is on the ground. And so you write it just like that. V4 is the start minus V1, which is my ground. I'm just going to put VG, whatever, divided by my 4 ohms, and that equals 0. This right here is the node voltage form of my KCL equation. These two statements are equivalent. It's just that one is expressed in terms of current. These are all still currents, but those currents are expressed in terms of voltage. You're just manipulating an equation to be represented in new variables. That's all you're doing. Keep in mind that VG equals 0. Okay. From here, I like to multiply my my equation by a number to get rid of the fractions. It looks like I'm going to multiply by 20. So I'm going to go, I guess I'll do it in blue, whatever. So I'll go times 20, and that's going to kill my fractions. So the 20 times the 10 is going to give me a 2. It's going to be 2v2 minus 2v4, okay, because 20 over 10, 2, and that 2 pops onto those guys. Easy enough. And then it'd be plus 20 divided by 5 is going to be 4, so I get a 4v3 minus a 4v4, okay. And then 20 over 4 is going to be 5, so I get a 5v4. But remember, that negative is going to hop onto him, so that's where that goes. And then what happens is you get a double negative because negative, negative. So that's going to give me a double negative, which gives me a positive. Oh, it doesn't matter now, does it? Because VG was 0. So that was convenient. But if it weren't 0, then I would actually have a positive value there. So now I have an equation that has V2, V3, V4. I just combine my like terms. 2V2 plus 4V3 minus 911 V4 equals 0. I happen to already know V2 and V3. So that's convenient. So I'm going to plug those in. So 2 times V2 was 8. And then plus 4 times V3 was 12. Equals 11 V4. So what I'll do is I'll just divide both sides by 11. And that'll solve for V4. So I got 16 plus 48 is what, 64? 64 over 11 is going to be my V4. Okay, let me just double check that because I did just definitely do it in my head. All right, so it'll be 16 plus 48. Boom. All right, so great. So 64 over 11 will be my V4. All right, so that's not a big deal. Now, I know each voltage. V2, V3, V4, and that's it. That's actually the answer. So we're good to go here. Now, of course, if I want to convert back to my original problem, which is to say I want to change my node, I can change my node now and still figure out the answer from here. Okay. What do I mean by change my node? I kind of got rid of the original ground and put the ground here. So if I swap the ground back, this is what's going to happen. I put the ground back in the center and I take it off of there. So what's going to happen is I get a V1, right? And V4 would end up becoming 0. That's not necessarily going to stop me from doing what I need to do. Why? Because if I knew V4 to the ground, right? If I look at it like this, let's put the ground back. If I put the ground right here, then V4 would be plus and the ground would be minus, and I knew that V4 was positive 64 over 11. All right. When I replace it, if I flip their places, okay, so I take the ground here and I reverse their roles, then what happens is now I put my V1 back here, and I'm now dealing with the ground. All that's saying is that if the top guy was 0 and this was 64 over 11, when I flip them, they're going to reverse places. That's what's happened. Because I flipped the ground, their voltages have to flip. And so what that means is V1 in actuality, right? V1 in actuality with respect to how I was doing it in the beginning is actually just going to be negative. So V1 is actually equal to negative 64 over 11 volts. And that's that. Okay? That's literally how that's done. It's not that really that's not that big a deal. A lot of students actually get tripped up on that, but don't let it get you. Okay, you flip the ground, you flip the nodes, and so I solved it my way, and all the answers are still the same. V2 is still gonna be 8, and V3 is still gonna be 12. Okay, it's just that my V1 and my V4 are gonna flip, because if you look at it like this, I can just put it into the equation form. Remember when I had the ground on this, on the O, on the V1, then my 64 over 4 would have been read like this. It would have been V4 minus V1 equals, and I know that that would have been 64 over 11. Okay, so in the first case, my V1 was 0, so I get V4 equals 64 over 11. However, I could write the same exact statement, because the statement is exactly the same, except I made V4 the ground. And what that means is V1 is negative 64 over 11. So that's a mathematical proof that kind of drives that home. Okay. And so that being said, I've solved for all of the voltage. Let's say if I wanted to take it one step further, and maybe I wanted to solve for the current right there, the current I3. That's not a big deal. I3, I'm sorry, not I3, I5, I'm sorry. So it'd be I5. All right, let's put it in, I don't know, let's put it in orange, sure. I5 is written like that. All right, they're the same. So I can easily just say I5 equals, and it'd be V3 minus V4 over 5. I know V3 is 12. V4 was 64 over 11 from my rendition divided by 5. It's not going to affect the answer. If I used V3 or actually no, that's just it. That's just it. This is going to be the answer no matter what. I don't want to go changing my placements, because then it'll mess me up. And I just have to solve it. So whatever number this would end up being, 64 over 11's a pain in the butt number. So let me just put it in my calculator. 12 minus 64 divided by 11. And then I divide it by 5. That current will be 1.24. That's amps. And that will be my answer. So if I wanted to find specifically the current associated, I can still use the no voltage representation to get my answer. It's just that I have to write everything in no voltage form. Now that I found all my no voltages, I'm good to go. And then I could just kind of plug and chuck from there. Okay, so that's that.